Hello students. So today's class we'll start off with spline shafts. So spline shaft has a number of key-like projections. As you can see in the figure here, there are many key-like projections. So these are called splines. They are integrated with it, and they're usually equally spaced around the shaft or around the hub. They are equally spaced corresponding to the recess here. Okay, and it is done simultaneously, like it runs simultaneously on both the hub and the shaft, and it moves in an axial direction. So one of the advantages is that it is self-centering. You can see it is axial, it is self-centering, and probably this much self-centering is not possible in keys. Okay, so therefore this device is used to transmit a higher torque than the key shaft, and of the same dimensions. So these are used for gradual engagement. You can engage and disengage so whenever the need be, right? So these are the terms used in the designing of splines. So P here is a small letter which denotes bearing pressure. H is the depth of spine. That is nothing but height. It's the difference between the major and minor diameter, capital D and small d. So major diameter is this, the outer diameter, and the smaller diameter inside, and height is just the difference between these two uh, by 2 is the average difference. So that's how much it is slotted inside. So capital D and small d, major and minor diameters. L is the length of the hub. It is this length, the through length of the entire uh, the key here. It's spline. So I is the number of splines. So small letter I is the number of splines. Right. So these are all the terms which we use in designing the spline shaft or even the hub. So for coming to the design procedure, you have just one formula to keep in mind: is torque transmitted by line shaft. So MT is the torque, half P, where P is the pressure, H is the difference between half the difference between the major and minor diameter, L is length, I is the number of splines, and again D minus H. So that is given. It is actually 17.20. I just stated that. It is 17.20. So this thing here is 17.20. Okay. It's not just 17. And spline shaft always designated by this number, I into D into D. So that's how you designate a spline shaft. And bearing pressure will be found in this table, 17.9. Okay, that's the table. So let's find that also. 17 and 9. The table. All right. Table 17.9. Where is the pressure? There is no pressure. Once D is known, we need to find length, breadth, and height. So L is 1.5 D. Let's see, L is length 1.5 D, and B is D by 4, and D is D or H. Let's say H. H is D by 10. Okay, so that's how you find. So first, write the governing equation. We knew the power is 2 pi nt by 60,000. So substitute and find what is the torque. The torque in Newton mm. So then you substitute torque and whatever given data in terms of D itself, and find the diameter that was nearest even number value, that's 52, and rest of the things just substitution, plain substitution. So you got 52 into 1.5, 78 mm is the length. Then 52 by 4, this breadth is 13 mm, that is the width. And 52 by 10 is nothing but the height, so 5.2. Right? Yeah, so that's it. So that's it with the uh, problem. Either you will be asked to find the power in case of the previous problem, or you will be asked to find the uh, dimensions as seen in this case. Right, so any doubts, you can let me know in the group chat. Let's move on to next. Okay, so that's enough for the problems with keys and shafts. So we have completed around 30% of the problem, 30% of this unit 3, module 3, that is. Let's start off with couplings. So couplings, there are two varieties. So I told you last class there are rigid and flexible couplings. Those are the two types of couplings. So mainly these are used to provide disconnections between the shafts and all, right? So first one, I'm going to talk about this muff coupling. So one in each category we will cover. So that is in case of rigid coupling, this we'll cover only rigid. So we are not bothered about this flexible coupling much. So rigid couplings are mostly used in industries and all those places. So in rigid, you have muff coupling. What we are going to cover is muff and flange type coupling. So in flange type, again, it categorizes the protected and unprotected type. So we'll finish this muff coupling first. So let's talk about the design procedure here. So each of these couplings, they follow a sequence of procedures. So first off, we will find what is the procedure. I'll describe the procedure, how it is solved. Next, all the problems whichever will come, it will just follow the same process. That is the same methodology or steps. Okay, what we have. Right. So let's start off. So step one in this muff coupling design is you design the torque. Torque transmitted, you can either use this equation, but this equation you see is present at chapter 2, that is 2.87b. Okay, or you can also use 2.nt, that equation 2.nt by power equation, 2.nt by 60,000. Here n is power, okay, and small n is speed. What we defined before is a little bit different. We can also use that equation. Okay. So it's just a simplified form. So we can also use, that is power P is 2 pi n mt by 60,000. So this was our general equation, right? So we can also use this. I hope you use this, because this reference will take off some time. Okay, instead of this, no, for step one. So instead of this for step one, so we just use this equation to find the torque mt. Okay, usually power will be given in the question. We need to find torque, and as we proceed, first step you find the torque, and then next you find the diameter of shaft. So diameter of shafts is cube root of 16 mt by pi tau d, and nu here. So all data are pertaining to this torque transmitted. Tau d is shear stress. Nu is the keyway factor. Keyway factor is 0.75, usually taken as 0.75. Okay, the most common value, and d is the diameter of the shaft which is connected. Okay, this is step 2. Find the diameter, and sometimes the diameter will be a random value. You will get 16.5 or 18.96, 200 point something. So like this, you will get different values of diameter. So we refer to this table to get the standard values of shafts. Okay, these are the standard values, how you extract. The ones in bracket are in, I think, inches. Okay, the ones outside, so that's the one in mm. Okay, we need to refer to those values. This is standard shaft diameters. The next step, that is step 3, is you find the outer diameter of sleeve. So muff coupling, let me show you how the muff coupling looks like. Okay, so this is the figure. You see this? This is the muff coupling over here towards the right side. Okay, so this is how it is placed. So you need to have D, keyway, and shaft, and this jib-headed key. So all of these is required to be designed. I'll just copy this. Paste it here. Okay, so this entire thing is required to be designed. Let me go back here. So this capital D, small d, H. So all these things are to be designed. So we need to know these dimensions. So that's why check out this muff coupling. It's very simple in construction. You just have a muff. There is the outer portion that's called the muff or sleeve. Okay, so this hatched portion you see is called a muff, or it's sometimes called even sleeve. So this engulfing the shaft, which is transmitting the power, and it is held in place by a key. So this is the key. Usually it is a jib-headed taper key for easy inserting and removal of that. Okay, step 2, you design the outer diameter. The outer diameter of that sleeve or that muff using the shaft diameter, and is also given in the equation here. And length of sleeve is given by, again, 3.5 times d, can given in equation just below the diagram. And we need to check whether this sleeve is capable of transmitting that power. So we take into consideration the shear stress and the torque both. Okay, also K, which is just a factor. It is just d by d. It's just some factor accounting for the hollow stress concentration factor. Now once if that this whatever shear stress we get using this equation, and whatever is given in the data is, if it is lesser, then it is safe, the design is safe. So that's why we check, because once we find the dimensions, because table dimensions are arbitrary, once we find that, only we can ascertain whether we can use that muff coupling or not. So step 4 is you design it based on diameter of shaft, that is small d. You check for the key width. So same like how we did in keys, like for crushing and shearing strength. So whatever we performed on the design of keys, so those two things we use, and again extract the dimensions of shear stress and crushing stress, and allowable stresses should be well within the values. So once we get the diameter D, so from D we can refer to this table 17.4 and get the dimensions of the key. So this is how the jib head key, which is used in muff couplings. So depending on shaft diameter, we need to extract the value of B and H. Okay, B and H, and then L will be same as that of the muff sleeve dimension. Okay, so both are same here. So L, I think we would have found already here. The same length we will apply for the key also, because it is running throughout the length. You saw in the diagram here that it's starting, it's running throughout the entire length of the sleeve. Right, so we'll keep the length as it is, and only we'll check for the allowable stresses for the key. Once it is within limits, we'll say the design of key is safe. So that's it for the design procedure of keys. Not keys, it's entire muff coupling. Okay. So let's start off this problem. How far we can go. So this is numerical. We need to design a sleeve coupling to transmit 10 kilowatts. So let's note down what is given. So given is power P is 10 kilowatts. Then speed is given N as 200 RPM. And the allowable values of shear stress, compressive stress, and key may be taken as 60 respectively. So shear stress tau is 60 newtons per mm square, right? And compressive stress, so sigma, is taken as, these are all allowable stresses, so it should not exceed these values, newtons per mm square respectively. And allowable shear stress cast iron sleeve. Okay, so this will be tau d, let's say 1. This, let it be d itself, and this is d1, which is 15 newton per mm square. So see what all these belong to. Allowable values for shaft. So these values are for shaft, and this is for sleeve. Because this is made up of cast iron, and this is made up of a different material. Maybe this is some ductile material, and this is I think very brittle material. So there's cast iron. That's why the shear stress value is low. So you need to use varied values for shaft and sleeve separately. Okay, can note this down appropriately before we start off the problem. Maybe this, and we'll move on to the paint box. So that's our data. Let's start off. So step 1. This is our solution. So in solution, we'll go step by step. So step 1 from the PPT. You can take screenshots at the time when I show the steps. Okay. So pick out step 1. It is torque transmitted. You need to find first what is it? Torque transmitted. Torque transmitted is, we can also use this equation which is in data handbook. We'll just modify something. So MT equals, so let's note this down. MT equals 9550 into P divided by N. Okay, small slight modification. What is that? Is N is power, which is in the data handbook, but we'll change N to P because we are familiar with the P value. So let's note it down as P, and small n we'll just put as capital N. Okay, so that capital N will be in terms of RPM. So whatever we have done so far is like this. And one more change is power will be substituted as in terms of watts. Okay, so that means it is 9550 into, our power was 10 kilowatts. So that means 10 into 10 power 3 watts divided by N, that is 200. Okay, you can use the old traditional one of 200, right? 200. You can use a traditional 2 pi nt by 60, but since this is in the data handbook, we can use this, but mind the notations. You don't get confused with the notations and stuff, right? So now from this, we'll get what is known as the torque. Okay, let's see this. It's a 9550 into 10 E3 divided by 200. So this is giving me a value 477.5 into 10 power 3 Newton mm. Right, that's our MT torque. Next, moving on, step 2. Step 2 from the PPT. We need to find the diameter of shaft. Right. Let's go for this diameter of shaft. So this is of shaft, not the sleeve. This is small d, not capital D. Okay. So this one is solid diameter. So it's cube root of 16 mt by pi tau d nu. So d is cube root of 16 mt by, what was that, pi tau d and pi tau d and nu. So we know mt is right here, pi we know, tau d. This is for shaft. Okay, don't get confused here. Tau d is 60, tau d1 is 15. So this is for sleeve and these are for shaft. We need to use this for shaft, that is 60, and the keyway factor nu is always taken as 0.75. Usually taken as 0.75. Nu is taken as 0.75. Okay. So this is equal to cube root of 16 into mt 477.5 to 10 power 3 divided by pi to 60 into 0.75. So this will give us diameter d. Okay, let's find out what is diameter d. So answer into 16 divided by 60.75 cube root of that. So I'm getting an answer 37.8 mm. Okay, so now this is not a standard value for a diameter, right? So therefore we need to go back to the steps and here. So from this we can extract the value of diameter. You can take a screenshot at this point showing the diameter. So it is for 35 discs we have a value, but after 35 we don't have any other intermediate value. So we'll push it off to 40 mm. So we'll keep d as 40. So from this is from table 14.6, standard value of shaft diameter. Right. So step 2 is done. So the next step, step 3, design of sleeve. So we know diameter, so we can find what is the outer diameter of sleeve, 2d plus 13. The next step 3 is dia of sleeve. There is d, capital D, and length L. Okay, so d is 2d plus 13. So d is 2d plus 13 given by equation 1945b. Okay, so that is 2 into 40 plus 30 This photos are 80, 93 mm. Continuing, we have length given as 3.5D. This is also given equation 1947. Okay, so that means it is diameter 40 into 3.5 times. So length will be 140 mm for the coupling sleeve. Okay, so now that we have the dimensions, we need to find, we need to check whether whatever dimensions we have taken, okay, is satisfying the conditions. Right? So let's say check for sleeve. Checking for sleeve, we are given as D equals cube root of 16 mt divided by pi tau d1 tau d1. So 1 is for sleeve, 1 minus k power 4, and this is given equation 1946. Okay, so we have mt, we have tau d, we have everything else. Only thing is we need to find this value of k. So k is d by d. That's just below the equation. So small d was, I think, 40 divided by capital D 93. So 40 over 93 is giving us 0.43. So if you substitute this, don't substitute that pi d, just substitute the diameter. So I'm just putting this d. So this is checking for the value. Let's see whether the shear stress is coming within or without. So 93 equal to, we have cube root of 16 into mt torque 477.5 into 10 power 3 divided by pi into tau d1 into 1 minus 0.43. Okay, so send the cube root over to that side, it will become 93 cube equals, let's multiply the entire thing here. So objective is our tau d1 value, that is the shear stress for sleeve, should not exceed the given limits. 477.5 E3 divided by this pi into 1 minus 0.43. So on the right hand side, I am getting like 4.27 into 10 power 6 by tau d1. So tau d1 is PQ on the answer divided by 93 cube. Okay, so tau d1 value I've got 5.3 Newton per mm squared. So if you compare with the original value, that is the limited value which is given, there is 15 for sleep, right? So this is well below whatever we have found, right? So that means we can say this is less than 15 Newton per mm squared. Therefore, design is safe. Design is safe. Okay. So this is half of the problem. We'll stop here and continue in the next class.